So everybody be with me. We have talked about computer components, about technology, a little about CMOS transistor, yeah? We talked about that. And then we talked one slide about the cost. Do you remember? The cost of the IC, which I've told you the cost is proportional to die area to the power of 2 or 3, something like that. Yeah, you remember that? Okay, now it is time to go to the main objective, the main criteria that you design. If each engineer is designing to make something better, to make a better performance of a device. So what is the performance of a computer, of a processor? What is the performance? Who is going to tell me? What's your idea? Could you tell me? The performance. When you say something, a CPU is better than another CPU, another processor.
So I guess the performance would include like the speed.
Perfect.
Oh, sorry, do you want me to keep going?
Yeah, what? Speed. First one is speed, okay.
And how well it can sort of, complete the, like the controls and stuff. How.
So it's somehow related to a speed, no?
Yeah, like how it processes like arithmetic and other, like it takes the input and whatever the system wants it to do, and then it processes the output.
So if it does something arithmetic well, it means that it can do it faster. Yeah. So you are saying about the speed, the time. Yeah. Anything?
What about like the number of tasks it can perform?
Who is that talking? Okay. Number of tasks?
Yeah,
yes. Number of tasks of what? During a specific time?
Yeah, like during
okay. So again, this is a speed. Number of tasks during a specific time. So it means the speed. Yeah. Yes?
Efficiency. So not overheating, for example.
So you are talking about the power.
Yeah,
power dissipation. Okay.
Yeah. So some CPUs overheat, for example.
Yes. So the other one is the power. So when you are making a processor and when you compare two processors, the one which dissipates less power is better because less power is better. Yeah. What else? But these are correct. Usually performance is calculated based on the speed, and power is also a concern. We have to make it better. Okay. Let's see an example, analogy in airplane industry, air industry. We have 4 airplanes, Airbus A380, Boeing 777, Concorde, and Boeing 737. Four airplanes. Which one is better? It depends on how do you want to compare it. Which one is better? I am talking about different criteria. Based on each criteria, we see which one is better, which one is first, which one is second. For example, the first criteria is passenger capacity. So you could put more passengers in one travel. So it's a good criteria, a good thing that we should consider. And in that one, Airbus is the best. Airbus accepts more than 800 passengers in the airplane. And then 777. Around how much? 300 passengers. Okay. The next one, for example, cruising range with one fuel, at a full tank, it should travel Airbus around 8,000 miles, 777 around more than 9,000, and Concorde around 4,000, and Boeing is around 3,000. So this is another thing that we should consider as the performance, as the better airplane. The next one is speed. Which one is going faster? And here Concorde comes. Concorde was a project maybe around, 30 years ago. They built Concorde thinking that it will dominate all the airlines because it is very fast. But it didn't. We can talk about it right now. But you see, Concorde, the speed of Concorde goes up to 1,300 miles per hour. But for example, Airbus A380 around 600 miles per hour. So the Concorde, which was about more than 2 times, they were talking about. I remember I was a kid at that time. They were saying that, okay, we created Concorde, and with Concorde you can go from Europe to States in less than 3 hours, something like that. I think that it was very fast. Okay. The next criteria, which I guess we tried here to make it something that accumulates the whole thing. Passenger throughput. How many passengers per hour with the time, the distance traveled, passengers, distance, time, all together, throughput of passengers. You see, with Airbus, it is around 50 passengers times mph, mile per hour. So in every hour, 50 passengers go 1 mile. You see, because what is important for us in airline industry, in air industry, is that you could make more passengers during less time, not just the time, not just the number of passengers. Together, the throughput is more important. So we calculated the throughput, and with this criteria, Airbus is the number 1. This is an example of when you are talking about the performance, you should think of what kind of criteria do you consider. Now, let's go to our course, to computer. When we are talking about the performance, as you mentioned, the time is very important. For example, you have written a MATLAB program here, or a Python program, and you run it, then it takes 2 hours to finish. The other processor executes that in maybe half an hour. So you are saying that this one is much better than the other one because it could have done my task very fast. So the time is the main performance criteria for us in computers. We call it response time. As soon as you ask the computer to perform a task until it finishes, this is the response time. You give a task and then you get the result. This is the response time. So how long it takes to do a task, this is important for us. The other kind of thing that we can consider is throughput, is the number of tasks per unit time. Total work done per unit time. This is the same, almost the same. The response time is the proportion to 1 over throughput, or throughput is 1 over response time. When we are designing a processor, how could we make these two better? Yes. You are going to design a processor. How would you do that? To make it less response time for the tasks, to a faster processor. What do you do? Just a guess, yeah.
I think using more effective ways to shorten the time and response.
How? That's the question. How are you going to shorten the time? You are saying the question again.
For example, using multiplexers, using some...
When you do multiplexer, it will be faster. How? Maybe you are saying that we are using multiplexer to do something in parallel, you know?
Yeah.
For example. That's bad. That's not bad. Parallel. You do it in parallel. What else?
Having more transistors in the CPU.
So a bigger processor, so it can do more tasks. Yeah.
Decrease the space between transistors.
So then what happens when we decrease the space?
Data goes
Faster.
takes less time to.
The delay would be less. When you put something from here to here, then it will be less delay. Yeah?
Use some predictive performance, like add something to allow the computer to predict performance.
Yeah. You borrowed it from the 7th grade ideas. That's right? Yeah, very good. Because in tasks, there are lots of times that the processor stops for finding the result of something. So instead of stopping there, halting, it can predict and then go and do it faster. Okay, that's very good. So one is that processor, a faster processor, a better technology, a bigger processor. The other one is putting more processors to do it in parallel. These things that we can do to make it faster. Now let's go and see the response time. We want to see, to analyze response time, so we can come up with ideas how to make it better. The first thing, the time, the execution time is important for us. So if you give the task to the computer and it takes 1 minute, and then you give it to another one, it takes 2 minutes. So this one is better than that one. This is 1 minute, this is 2 minutes. So we've defined the performance of 1 over execution time. Whatever execution time is less, the performance is more, is better. Let's say X is n times faster than Y. The computer X is faster than Y. It means that performance X compared to performance Y is more. Or execution time of Y is more than execution time of X. It is reciprocal. So, and we calculate the relative performance, which would be n. And if X is n times better performance. For example, 10 seconds, a program takes 10 seconds to be executed on A, machine A, and 15 seconds on machine B. So which one is faster? This is 10 seconds, this is 15 seconds. So 10 seconds is faster. How much? In which relation? In which ratio? Ratio is 15 to the 10 is 1.5. So machine A is 1.5 faster than machine B. Very obvious. So A is 1.5 faster. If we want to calculate the time, there are 2 times that we could consider. One is elapsed time. You, for example, press the enter on the computer and then wait until it finished and say, okay, it took 5 seconds. This is elapsed time. This time consists of so many things. The input, you put input, maybe output. So during your program, it will refreshing something on the display. It might connect to the internet at the same time the computer is connecting to internet. At the same time, it is loading something from the hard disk, and so many other things, plus the things that is going to be done in operating system, because you are executing something and the operating system is taking care of so many things. Well, it is processing, I/O, OS, and sometimes nothing is done, it's just idle, it's waiting for something to come up. But these the whole things. And this is some kind of system performance, not our task, the task that we wanted to find out how long does it take. The other one, which is just focused on our task and to see how is CPU doing, because we are more concerned right now in CPU processing. Our course is designed to is to design a processor, a CPU, not the whole system. The whole system, I/O, so many things. We are not concerned about that right now. The CPU time is the time spent processing a job, just that job, not the other things, I/O, OS, so many things. And so we should somehow remove the I/O time, other jobs, and so on. So you can compare these two: a system time, CPU time. They could both of them are something that you could consider that you make which one is better. You make them better. But right now in our course we are focusing on CPU time. So we are going to CPU time. The first thing that we talk about CPU is clock. Everybody knows that the processors, all of them are working with a clock. For example, this laptop has a CPU and it has been written that the clock is 1.2 gigahertz. 1.2 gigahertz frequency of the clock. So what does it mean? It means that there is a clock which everything is synchronized using this clock. And at the edge of the clocks, the tasks are done and the state is changed. So during the clock cycle from this edge until this edge, the tasks, the calculations are being done. And it takes time, add, subtract, or, and so many things. But at this time, the state is going to be updated. So it should be ready at that time. But this is a very important factor, cycle time, for making the CPU time. Whatever the clock is longer, then it takes more time to run a task. Whatever it is shorter, so it means that it is faster. Okay. So the first thing is we talked about the clock. And clock period is this, from one edge to other edge. And then it repeats. This is the clock period, duration of the clock cycle. For example, let's say that here we have a clock period of 250 picosecond or 0.25 nanosecond. 250 picosecond, 10 to the minus 12. So if this is the cycle time, what would be the frequency? The frequency is the reciprocal of that. How much would it be? 1 over 250 is some kind of 0.4, 4, how much? 4 gigahertz. 4 gigahertz. So the frequency of this clock is 4 gigahertz. 4 giga. 4 giga means 4 times 10 to the 9 hertz. And it means in 1 second, there are 4 billion cycles. 4 times to the 10 to the 9. 4 billion cycles. Okay. Now that we have talked about the CPU time, then when you execute a program, it takes a specific number of clock cycles, and that's it. There is a number of clock cycles. We don't have, for example, half a clock cycle or 2 nanoseconds. No, we have, for example, 100,000 clock cycles is taking this program to be executed. So it is a factor, a multiply factor of clock cycles. So you can say CPU time is the number of clock cycles that the CPU takes time times clock cycle time. Our clock cycle time was 250 picosecond or 0.25 nanosecond, and this program we give a program. For example, you execute a MATLAB simulation, video coding, something, and it takes, let's say, 2 billion clock cycles. So 2 billion clock cycles, time 0.25 nanoseconds, it goes to 2 times 2 to the 5. It will be half second. 2 billion clock cycles times 20.25 nanosecond. It will become half second. Okay? Or if we said that clock cycle time is the reciprocal of the clock rate, the frequency. So you could say CPU clock cycles divided by clock rate. They are the same. Either times clock cycle time or divided by. We could say 2 billion clock cycles divided by 4 gigahertz our rate. It will be the same. It will be 0.5 second. Now, if you look at these things, it will give us more information. If you want to make something faster, the CPU time less, then when there is a division, you could either decrease numerator or increase denominator. Okay? Either we should turn the CPU clock cycles down, decrease that, or we should increase the clock rate. As you told, I guess, you told us that you could have a better clock frequency, a faster CPU, which has a better clock rate. This one is 1.2 gigahertz. This one is, for example, 2 gigahertz. So this is one thing. You could increase the clock rate. The other thing is that you decrease the number of clock cycles. So how do we do that? We are going to talk about that. The performance would be either reducing number of clock cycles or increasing clock rate. Both of them could work because it is a division. Division, you can decrease there or increase the denominator. Hardware designers, so they should think about that. We want to make this, decrease that one, increase that one. Could we do this at the same time? If I want to decrease CPU clock cycles, it means that I should have a processor which has a more complex circuit which can do the things in less clock cycles. This computer, for example, is doing this in billion clock cycle. If I wanted to make it less and make it, for example, 500 million, then my processor would be more complex. Isn't that right? You make it more complex to do more things in one clock cycle, so it will make the clock cycle, the number of clock cycles less. So if you do it more complex, if you design it more complex, it means that the clock frequency gets lower. It is very important. I'm sure that you haven't designed something to see this in the real thing. That I hope that we could do it later in our course. Because when you do it something more complicated, then you are actually making the clock frequency lower because the delay would be more. And when you have more delays, it means that the frequency, you know, here I showed you. the tasks should be done in this period. So at that time, everything would be ready to go to the next state. And again, this one. When you do more tasks, you want to do more complex tasks here, then it means that it should be wider, it should be longer, and then it means that it should be lower frequency. So here, this is the sentence here. Hardware designer must often trade off clock rate against cycle count. When you want to decrease the cycle count, then you have a lower clock rate. When you want to have higher clock rate, then you have to simplify your design, then the cycle count would be more. So this is something that you should compromise, you should trade off. Which one you want to do? Questions? Okay, this is an example. We have a computer A, has 2 gigahertz clock, 10-second CPU time. So a program took 10 seconds. So we can calculate how many clock cycles did it take. 10 second, 2 gigahertz clock cycle. 10 second, 2 gigahertz, 2 gigahertz clock cycle is how much? 10 to the 2 is 5. 5 times 10 to the 9. So it is 5 billion clock cycles. This program, which took 10 seconds, based on this clock cycle, actually means 5 billion clock cycles. Okay. Now we want to design computer B, which should finish the task in 6 seconds. Okay, we want to make it faster. Instead of 10 seconds, we want to make it 6 seconds. But when we are doing so, the CPU gets complicated. And when the CPU gets complicated, the clock rate would be more. The clock rate would be less. The cycle time would be more, would be larger. How much? 1.2 clock cycles. So the clock cycles of the previous one, the A computer, times 1.2 is the clock cycle of the computer B. So if this is the case, with this clock cycle, with that task, how many clock cycles, what would be the frequency, the clock rate to make it in 6 seconds? Okay, we calculated it was 5 billion. Now you divide 5 billion by 1.2 times 2 gigahertz. This is 1.2. The clock was 2 gigahertz. So the new clock, the new clock would be 2 divided by 1.2, and then the whole thing was 6 seconds. If you calculate that, it will be 4 gigahertz. You need a clock rate of 4 gigahertz. This one was 2 gigahertz. This is 4 gigahertz. We doubled the frequency of the clock, but we reached a point of only 40% improvement. 10 seconds became 6 seconds. Why? Because the clock rate couldn't go fast. The clock rate couldn't be as much as possible that we wanted. Yeah. CPU times the CPU time clock rate. Yeah, CPU time clock rate is 10 seconds times 2 gigahertz. What? We divided. Oh, wow, we did a mistake. Oh, we divide 10 seconds times 2 gigahertz. Then the time, CPU time by clock rate. We should divide it by clock cycle, and we should multiply it by divided. I did something wrong. So it is 20 clock cycles, and these clock cycles, we wanted to make it 6 seconds. So the clock rate should be 4 gigahertz. Now we talked about clock cycles. We talked about clock rate. But what is making the clock cycles? The instructions. You have a program. In program, you are saying that add this by this, then multiply this, then divide this, then and this, then or this. There are lots of instructions that you are writing in your program, and it is going to be executed. So these instructions are executed, and each one takes a number of clock cycles. For example, add takes 1 clock cycle to be, multiply takes 4 clock cycles to be executed, and so on. So different instructions are getting the clock cycles. So we can say clock cycles, the number of clock cycles that we get is the number of instructions that we are executing times the number of cycles per instructions. If all of the instructions have the same cycle per instruction, for example, all of the instructions takes 2 clock cycles, then 2 clock cycles times the number of instructions would be the clock cycles. But it is not the case. Add takes shorter than multiply. Multiply takes more clock cycles to be executed. So we have to separate them. The number of add instructions times 1 clock cycle plus the number of multiply instructions times 4 clock cycles, and so on. So if just consider the average cycle per instructions times the instruction count becomes clock cycles. So if we look at the CPU time again, now we have a very new equation. Instruction count, the number of instructions should be executed, times CPI, clock per instruction. Each instruction, how long does it take for each instruction? Divide by clock rate. So this is the new equation. And now it gives you an idea if you want to make a better CPU time, a lower CPU time, which is our objective. Our goal is to make it faster. Then either you have to lower instruction count, you have to lower CPI, clocks per instruction, and you have to make higher clock rate. So each one of 3 needs different design methodology. If you want to make CPI less, you do something. If you want to make a larger clock rate, you do something else, and so on. So these 3 would be something that it will be among us, in front of us, in all the course, that we are either trying to make the number of instruction less, instruction count, or CPI, clock per instruction, less clock per instruction, or we are making something, a better clock rate. So instruction count for a program is what makes the instruction count our program. If you are doing a video coding, it has a number of instructions. If you are doing a MATLAB simulation, another kind. If you are doing, for example, a word processor, writing a word processor like Microsoft Word, it has another number of instructions. So it determines it by program, and then instruction set architecture. Did we talk about instruction set last time? Maybe just a reference. Because when you write, for example, you want to add something, then this add in high-level language in C, we talk that it goes and become a machine language for the processor. This translation depends on ISI, instruction set architecture. Based on the instruction set that you have, each high-level language compiled to low level, and the compiler will do that. So if we have a better compiler, then it might translate a high-level language to less instructions. Or if we have a better instruction set, then the number of instruction would be less for each program. The other thing is the number of cycles for instructions, which affects that, which is this one is based how this one is calculated or affected. What do we have in processor if we want to make the average cycles per instruction less? What should we do? How could we do that? You should make a better hardware. This is the hardware. So this one was program, instruction set, and compiler to make the instruction count less. But when you have an instruction, you have an add in lower level, not add in the C language. When you have an add in lower level, you add 2 registers, then how many clock cycles does it take to calculate the sum? It depends on the hardware. One hardware might take 1 clock cycle, the other one might take 2 clock cycles, and other things. So, and also different instructions and different CPI. We are usually calculating an average one. For example, let's see an example. Computer A cycle time is 250 picosecond. That's the one that we had, 4 gigahertz clock cycle. And the CPI, the average CPI is 2. It means that per instructions, we have 2 clock cycles for each instructions to be executed. We have clock CPI of 2. Computer B, 500 picosecond, it means 2 gigahertz. The clock is 2 gigahertz, but the clock per instruction is less because it has a better maybe architecture. It is a better architecture, so it is 1.2. 1.2 clock per instruction in average. For example, it might be 1 for sum, 1 for add, 4 for multiply, 3 for branch, and so on. The average would be 1.2. Both of them have the same ISI, yes.
I was going to ask, is there like a unit of measurement for CPI, or is it just kind of like an average?
This one is average because all of the instructions, they don't have the same clock cycles.
Right.
Add takes 1 clock cycle, but multiply takes 10 clock cycles. Divide might take 20 clock cycles because divide is harder, more difficult. We will talk about this. But so it is an average. So we calculated, we had a program, we gave them to computer, we counted the number of clock cycles and say, okay, it had this number of instructions, this number of clocks, so the average would be 2 clock per instruction. Both of them have same ISI, so it means that they have the same number, the same instructions. So which one is faster? How do we find out which one is faster? CPU time was how much? Instruction count, number of instructions, time CPI divide by clock rate, okay? Here, clock rate, we have clock rate, let's see. Computer A has clock rate of 250 because 4 gigahertz. Computer B has 2 gigahertz. Okay. Instruction count. Instruction count is the same because they have same ISI. A program, when you give a program to both of them, because they have the same instruction set, they have the number of same instruction count. So we say instruction count here, instruction count here. So instruction counts times CPI. Now machine A CPI was 2, machine B CPI was 1.2. Let's calculate. IC times 2 of 4 gigahertz. We keep the gigahertz because we want to just make the relation. See how much this is more than that one. So gig, I remove gig here, I remove IC here. So it is 2 to the 4. It is 1 over 2. And this is 1.2 over 2. Which one is more? 1.2. So if we this is 1 over 2, 1 over 2. This is 1 over 2. This is 1.2 over 2. Which one is more? Is greater? This one, 1.2. So the CPU time of B is more than the CPU time of A. So it means A is faster. By how much? By 1.2. This is 1.2, this is 1. So CPU A is faster than that. Okay? CPU time B is to the CPU time of A is 1.2. We tried to show you the number of factors which make CPU time. Instruction count, CPI, clock per instructions, and clock rates. So A is faster. CPI, I told you different instructions take different number of cycles, so you should calculate them separately or take an average. For example, if you have, you see here, sigma of CPI times instruction. If you have 5 add, which each one of them is taking 1 clock cycle, plus 6 multiplication, each one of the 4 clock cycles, then you have to calculate this as the CPI, the number of clock cycles. 5 add times CPI of add, which is 1. 6 multiplication times CPI of multiply is 4. Each multiplication takes 4 clock cycles per instruction. So this is how you calculate. And then if you divide this by the total number of instructions, then you get the average CPI, relative frequency of each one. For example, we have 2 alternative code sequence using instructions in classes A, B, C. We have 3 different classes of instructions. For example, this one is add, this one is multiply, this one is branch, for example. For class A, CPI is 1. For class B, CPI is 2. For class C, CPI is 3. It takes 3 clock cycles per instruction. We compiled our program with different compilers. One of them gave us this sequence. The other one gave us this sequence. One of them gave us 2 A class instruction plus 1B, 2C. The other one, which compiled, gave us 4 class A, 1 class B, 1 class C. Which one is faster? We should see. Which one is faster? Okay, we have CPI of 1 for A, and in sequence 1, we have 2 of this. So 2 times 1 is 2 for these 2 clock cycles. 1 times 2 is 2 for that. 2 times 3 is 6 for that. So we have 6 clock cycles plus 2 is 10 clock cycles for sequence 1. Clock cycles, no, instruction count. 10 instructions for clock cycles. Yeah, clock cycles. That I was right. This the next one. 4 class A. I see 4 class A. I forgot. Class A. Okay. CPI for class A is 1. 4 times 1 is 4 clock cycles. And 1 class B, 1 times 2 is 2. And 1 class C, 1 times 3 is 3. 3 plus 2, 5 plus 4 is 9. So the sequence 2 is a better code. The compiler which made the sequence 2 is better. We didn't know at the beginning. We had 2 mix of instructions, and we calculated which one is better and with how much you can compare them together. Okay, again, CPU time is number of instructions times number of the CPI, number of clock cycles per instruction, instruction count, CPI, and clock cycle, clock rate. or clock cycles is better. Clock cycle or TSTC. The IC, CPI, TC. This is what we have talked about. Performance. Okay. Now let's think about this. You have different algorithms to do something. You have different programming languages, and you have different compilers. You have different instruction set architecture. Each one of them makes different of each one of these three. For example, if you have better algorithm of doing something, for example, you have a quick sort and a bubble sort for doing something. If you have different algorithms, then the number of instruction will be changed because you changed your program, so it changed. Yeah. So IC is affected by algorithm. And also possibly CPI, because when you have different algorithms, you might have a different mix of instructions. This algorithm makes more multiplication, this algorithm makes more addition. So this one would be better than this one because it is a better mix of instructions. For programming languages, you are using C, Python, or Basic, Fortran. You don't know Fortran. So again, based on the programming language, you are compiling the high-level language to low-level, and based on that, the number of instructions will be changed. And based on that, again, the mix of the instructions, we have different mix, and the CPI would be different. Compiler, of course. Compiler, again, the same thing as programming languages. If you have different compilers with one language, you are writing in C, but you are using two different compilers. This will compile in a different number of instructions, and it will cause different number of CPI. An instruction set architecture, it depends on the vocabulary that we have talked. You have a code, and then you will make it to the lower level of the machine. So if you have different set of architecture, of course it will change the IC. If you have a rich instruction set, which each instruction does complex things, then the number of instructions would be less. Let's say, for example, you have an instruction which adds and multiplies together. Multiplies and add, two things. So it will be one instruction compared to the other instruction set which it doesn't have this instruction. It has add separately, multiplication separately. So it is the different number of instruction count. And then again CPI and TC. Why TC? The clock cycle, because when you have different instruction set architectures, then it means for executing these instructions, as my example I have to do, this instruction has add plus multiply together. The other one doesn't have this instruction, just has add and multiply. So this machine is more complex. And when this machine is more complex, you have to design more circuits, more complex. And I told you in the previous slide, when it is more complex, it means less clock rate, because you have to do so many things and it will slow down the CPU. So the TC is also affected here. So now, up to now, we talked about speed, time. And as you told, somebody, I guess, talked about power. Power is also important right now. Because everything, if we are talking about embedded device, it runs battery. If we are talking about data center and servers, so it is lots of powers. For example, Google data centers, I don't know how many how many watts they are consuming, and there are a lot. For Bitcoin miners also, I guess you have heard that you were using using so many computers to mine Bitcoin, and it takes power. So power is important right now. I will talk, and it gets more important in CPU design. You look at this diagram, this figure. There are two things here: clock rate, which is the blue one, yeah, and the power, which is the black one. And it is about 1982 to 2018, around 30 years, around 30 years. And it will show us the different generations of Intel processor. It started from 80 to 86 to Core i5 in 2018. If you look at them, first up to here, which is a Pentium 4 processor. Up to here, the clock rate is increasing with a very good slope, almost doubling every 1.5 year. And also the power is going up. It consumes more power. And it reaches 103 watts for Pentium 4 processor, which is a large power consumption. And this power consumption needs to be cooled. You have to have heat sinks to put on the processor. You might need to have some kind of cooling mechanism to make them cool. Have a fan in your computer and so on. So cooling down the CPU, the processor, was hard for Pentium 4. And as you could see, at this time, they could have almost reached the maximum power dissipation for a chip. We might have more power in specific chips, but with, for example, a cooling mechanism of liquid nitrogen. Yeah, so that's very expensive. But for personal computers, we cannot use that kind of cooling system. But here it stopped. And then you see in the next generation, Core 2, in 2007, the power decreased. Why? Because they changed the Pentium 4 processors to two smaller core processors. Pentium 4 changed to two simpler core processors with simpler instruction set, with simpler design, which makes them lower power. You see, this is the design that they have to think about this. But what did they do? They made it two cores. So from this time, we moved from single core processor to multi-core processors. We have multi-core in each processor. For example, this one is Core 2 at 2007. For example, Core i5 has 8 cores or 4 cores, 2 versions, I guess. 8 cores. And so we changed from single core to multi-core. And it made the power less, and you could see even during the years it became less and less. And again, then here we try to make a better processor. So at maybe after how many years? 2007. After 11 years, we reached the power at that time. Well, it's very good in terms of the design. And again, you could see the clock cycle didn't go higher. Moore's law was predicting that every 1.5 year, it should be doubled the clock rate. And it was true for this period. But later, because of the power, the main important thing is power. Because of the power, the clock rate didn't go high. Why? Because in CMOS that I've showed you last time, the power is mainly due to dynamic power. We have static power and dynamic power. Static power is the leakage in the IC when there is I current times V It is a static time, which in CMOS technology is very low in CMOS. But dynamic power is this. Power is C times V to the 2 times frequency. You know, the equation for energy is half CV2. I guess you know this equation. 1/2 C capacitance times V to the power of 2. This is, I think that you, maybe in the physics of your high school. 1/2 CV to the 2. Okay, if you, this is energy. Energy during a unit time would be power. So if you have F here, F frequency. Frequency is 1/T. If you have F here, then it will be power. Power is C V to the 2 times frequency. And during this time, you see the frequency got 3000 compared to 12. It is about how many? 12. So it was around 4 times. It is around 1,000 times. The frequency got 1,000 times, but the power only 100 to 3 times, 30 times. Power increased 30 times, which frequency was 1,000 times. Why? Because the voltage came down. Because voltage came down from 5 volts here to 1 volt here, and the frequency came 1,000. Capacitive load also decreased, so the power around 30 times. So this is the technology that happened. Okay, it is time now. We talked about the performance based on CPU time. Now we are looking at the power, to how to make the power less, and talking about a little about power, and I guess that will conclude our chapter 1. So in chapter 1, we try to give you a big picture of what's happening in the computer architecture world. From the next chapter 2, which will start the next session in Friday, we go to instruction sets. We are going to see how would be an instruction set, and when we have instruction set, how are we going to design our processor based on this instruction set. Okay? Have a good time. Thank you.